All right, this is a video tutorial for the Big Ideas Geometry section 5.3, Proving Triangle Congruence by SAS. The major idea is that you can use the side angle side congruence theorem. That's what your SAS is going to stand for today, and be able to use that side angle side theorem to solve real life problems. So first major idea is in order to prove two triangles are congruent, before now, all you have known is that you need all three angles and all three sides to be congruent. You match up all of your corresponding parts and you get 6 different parts of a triangle are congruent to prove that the whole triangles are congruent. Well, if we start to incorporate our third angle theorem, use some ideas of some isosceles, equilateral, right triangles, there could be a couple shortcuts that we don't need all 6 parts to prove a triangle congruent. And this is the first one that we're going to go over in this video. So if 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of a second triangle, then both of the triangles are congruent. So notice how this first triangle ABC, you have 2 different sides that are marked that they're congruent. We have AB and AC. Same thing over here, DE and DF. Those are marked congruent to each other. And the included angle, which means the angle that is touching both of those sides, angle A is touching both AB and AC. Angle C is not included because it's not touching this line segment B. Included means in between or touching both of the sides. So the order is also going to help when we go over some other of the triangle congruency theorems. SAS, the A is in between the 2 sides in that order. It's not SSA or ASS, it's SAS, where the A is in between. So included angle is in between 2 sides and an angle. So let's write the proof. In this 2 triangle diagram, we're given that line BC up at the top is congruent to line DA, and that line BC is parallel to line AD. So we have both markings for congruency and for the lines being parallel, and we need to prove that triangle ABC is congruent to CDA. Remember, the order matters, so it's going to tell us which parts are corresponding to which. So let's get our 2-column proof going. Statements on the left, reasons on the right. Put our given information down first. That line BC is congruent to line DA, and that is our given reason. And one thing that's going to help you keep track of how you can prove by SAS is if you write the letter S next to something where you've proven sides are congruent, and the letter A next to something where you've proven angles are congruent. That way you can go back all the way through and make sure you have all 3 of those parts proven, and then you can prove that the triangles are congruent. So this first one, you put the letter S because they're sides. Then you're given information about line BC and line AD. And because they're parallel, that does not mean congruent. So we're not going to write the letter S there. We only write the letter S if you see this congruency symbol right here. So based on these 2 lines being parallel, one of the big focuses from chapter 3 was our angle pairs. So because these lines are parallel and you have a transversal, we can use the alternate interior angle theorem to prove that angle BCA is congruent to angle DAC. And notice how they're also now marked on the diagram. Since these 2 are parallel, and you have this transversal that is cutting them, you know that the alternate interior angles, where they're on the opposite sides of the transversal, are congruent to each other. So we can put the letter A next to that those 2 lines are, or those 2 angles, sorry, are congruent. And then we're next going to use the reflexive property of congruence and say that a line is congruent to itself because those 2 triangles share line AC. You're going to say line AC is congruent to line CA, which is the exact same distance. They're just in different order depending on the direction you travel. And that is a pair of sides. So now since you go back through and you have side, angle, side here, you can write a triangle congruency statement based on what you need to prove triangle ABC is congruent to CAD. And again, remember that these corresponding parts match. So you got angle A is congruent to angle C because those are first. and you have BC and DA. BC are 2 and 3, DA are 2 and 3, so all those are in order correspondingly matching. Okay, so we have two more triangles where there are two lines that are passing through the center of a circle. And what can we conclude about triangles MRS and MPQ? Well, because you have two lines that are passing through a given point, the opposite angles that are across from each other are vertical angles, and those two are going to be congruent to each other. So that would be PMQ right in here, and RMS, which is right in here. So go ahead and mark those as congruent on the diagram. And since all points on a circle are the same distance from the center, if you draw a radius from anywhere from the center to the edge, that's the definition of a circle. So all those lines are the same distance. So you can say any line from the center to the circle are congruent to each other. So you can go ahead and mark that SM is congruent to MQ, RP or RM is congruent to RP. All four of those are actually congruent. So you now have two pairs of sides and the angle in between them. So triangle MRS and MPQ are congruent based on the side angle side congruence theorem. All right, solving your real life problem now. You're making a canvas sign that you're going to hang on the triangular portion of the barn wall, and you think you can identify two identical triangles that are going to make up the shape of your canvas. You do know that RP is perpendicular to QS, or that they form a 90-degree angle, and that the distance between QP and PS are the same. That's like your midpoint theorem. You're taking the halfway point between your two edges of the barn. And we need to use the SAS theorem to prove that those two triangles are going to be congruent to each other. So let's see if we can identify two sides and the angle between them. So we are given that PQ is congruent to PS, so that's one pair of sides. Based on the reflexive property of congruence, RP is the same as itself. Those two triangles are bumped up next to each other and they share the same side, so that's the second pair of sides. And then we have right angles because they're perpendicular lines. RPQ and RPS are both right angles, so those two angles are congruent to each other and they are in between your two sides. So because you have two pairs of sides and the included angle, the triangle PQR is congruent to PSR.